electronics. So in this video we are going to see about all major type of oscillators. So this is a quick revision video of oscillator circuit, mainly on exam point of view. Okay, so we'll be seeing what is the basics of oscillator, what are the various important oscillators. In this video we are going to discuss about feedback oscillators, that is Wien bridge oscillator, Hartley oscillator, Colpitts, Clapp, phase shift oscillator. So these type of oscillators we are going to see. First, before going into that, let us see what is an oscillator. Okay, let us see the very basics of oscillators. Oscillators are circuits which can generate output without necessarily an input signal, or we can say that without an input it generate output. It generate output waveforms. It can be sinusoidal, square wave, or sawtooth. Okay, depending on the circuit. Now, there will be DC supply given to it, but there won't be any input given to it. Okay, so without any input, it generates output. Such a device or a circuit is called an oscillator. Now, the oscillators can be broadly classified as oscillators with feedback and also relaxation oscillators. That is feedback oscillators or relaxation oscillators. So, feedback oscillator means there is a diagram over here. You can see there is a triangle which is an amplifier, and the output of the amplifier is given to a feedback unit or a circuit, and then it is fed to the input. So this circuit is called a feedback oscillator. That is an amplifier with a feedback circuit. You cannot see any input waveform here, but this will be generating output waveforms. Okay, so this is a feedback type of oscillator. So a part of output is fed to the input, and we know that in oscillators we'll be using positive feedback, and in amplifiers we use generally negative feedback. That is another important concept. So oscillators use positive feedback. So this circuit will be a positive feedback circuit. Then outputs will be most commonly sine waves are generated as outputs. Then, if you discuss the case of a relaxation oscillator, there is no feedback. RC timing circuit is used to generate a waveform. Okay, here the outputs are generally sine wave or square wave. Now, moving on to a very important concept of feedback oscillator. Consider this circuit. There is a amplifier with a gain of AV, and there is a feedback unit with a feedback factor of beta. Now, this feedback unit is feeding the signal to the input of the amplifier, and the overall closed loop gain is ACL. Okay, and in order to have sustained oscillation, so the oscillator circuit will be creating oscillations, right? So in order to have sustained oscillations, the closed loop gain or ACL should be equal to AV beta, and that is equal to 1. This criteria, I hope that everyone has heard of this criteria during their early studying time of engineering or diploma or anything. This is called BARC criteria. So in order to have sustained oscillations, the gain product or with the feedback factor, it is a product of gain and feedback factor, should be equal to 1, or it should be greater than 1 for a startup of oscillations. Okay, so it should be equal to 1, which is called a BARC criteria. Okay, so this is the basics of oscillator. So consider or just know that oscillators are devices which give output without any input signal. Now the broad classification is feedback type of oscillator and a relaxation oscillator, and a feedback type of oscillator will be having a very basic structure like this. Will be having an amplifier and a feedback circuit. This feedback circuit will be varying according to the various type of oscillators, and also for the amplifier circuit or amplifier area, we can have either BJT configurations. That is, we can use either bipolar junction transistor type amplifier circuits or FET type amplifier circuits. Both can be possible. Okay, so it actually depends on the various type of oscillators. Okay, next we are going to see about some of the classifications of feedback oscillators. The first type of oscillators that we are going to see is RC feedback oscillators. Okay, The main type of RC feedback oscillators are Wien bridge oscillator, phase shift oscillator and twin T oscillator. Now when I'm saying RC feedback means, just imagine that the feedback circuit is having a combination of R and C, that is resistors and capacitors. It's various combinations. Okay, so that is called an RC feedback oscillator. Simple, right? RC feedback means the feedback circuit consists of RC units or resistor capacitor combinations, and their frequency of operation, that is for up to 1 megahertz, these type of RC feedback oscillators can be eligible or can be used. Okay, the first oscillator we are going to see is Wien bridge oscillator. So we'll be seeing all these oscillators in an exam point of view. If you want a detailed video of any of these oscillators, please do mention in the comment section. We'll be doing an entire video on that oscillator itself. Okay, so the first one is a Wien bridge oscillator. Now, Wien bridge is a familiar term to everyone. What is actually a Wien bridge? Wien bridge is actually used for expressing the value of an unknown capacitor, or it is used for measuring capacitance in terms of resistance and frequency. So you can see here there is combinations of resistors and capacitance, and if you want to find an unknown capacitance, generally it will be connected in this branch. Okay, C1. Here it is C1. If you are using this as a bridge only, it will be CX. This is RX. So just know that this Wien bridge is generally used for measuring of capacitance in terms of resistance and frequency. Also, it is used for measuring of radio frequencies. Okay, and this is the bridge balance equation for a Wien bridge at a frequency this. Okay, so we'll be seeing about it. So just know that a Wien bridge oscillator is consisting of a Wien bridge as a feedback circuit and a op-amp as an amplifier stage. So this combines the amplifier and the feedback unit. Very easy to study. Just you should be knowing that this is the structure of a Wien bridge. So this is the amplifier stage, this is the feedback stage. Okay, just always whenever we are studying feedback oscillators, have the basic structure of a feedback oscillator in mind. It is having a amplifier unit and a feedback factor, or a feedback unit with a feedback factor of beta. Okay, here this is Wien bridge, which is a feedback unit. This is the amplifier stage. So it consists of an op-amp, and the terminals of this Wien bridge is connected to the inverting and the non-inverting terminals of the op-amp. And this forms the amplifier stage, which will give you the output. So the concept of using a Wien bridge oscillator is that it uses a frequency selective bridge to provide a low distortion sine waves. Okay, so when we are using a Wien bridge oscillator, it is actually using a frequency selective bridge which provides low distortion sine waves. So from this, it is clear that Wien bridge units or Wien bridge oscillator generally gives sine wave as its output. Okay, now when the frequency is f0 equal to 1 by 2 pi square root of r1 c1 r2 c2, just have a just Google about Wien bridge. You can see that this is the general frequency equation for a Wien bridge. There you can see Cx, Rx terms, because Wien bridge is used for finding capacitance. So it will be X means unknown terms it will be. So when the frequency is this, then the bridge is balanced, and this is the bridge balance equation. That is R3 by R4. This is R3, this is R4 is equal to R1 by R2 plus C2 by C1. Okay, so this is the concept, or this is the criteria for a Wien bridge. When the frequency f0 is f0, then the bridge is balanced, and this is the bridge balance equation. Okay, now when R1 equal to R2 equal to R, consider the resistors are identical and the capacitances are identical. That is R1 and R2 is equal to R, then C1 and C2 is equal to C. Then the equation is reduced or deduced like this: f0 is equal to 1 by 2 pi RC and R3 by R4 equal to 2. Okay, so the concept is that R3 by R4 should be greater than 2 for sustained oscillations. Okay, If R3 by R4 is greater than 2, then it will produce sufficient loop gain for the circuit to oscillate at the frequency equal to F0. F0 is equal to 1 by 2 pi RC. So if R3 by R4 is greater than 2, then it will have sufficient gain to oscillate at this frequency. Okay, I hope the concept is clear. And also, the minimum gain of this amplifier stage should be greater than 3, or it should be minimum 3. So the amplifier gain should be normally greater than 3. So these are the important concepts of a Wien bridge oscillator. I hope the concept of Wien bridge oscillator is now clear to you. So Wien bridge oscillators are generally, if you say about Wien bridge, it is a RC phase shift oscillator, and up to 1 megahertz we can use Wien bridge oscillators, and you should be familiar with the circuit as such, and also you should be knowing what is the frequency of the feedback circuit and what is a bridge balance equation and what should be the value of R3 by R4 for having sustained oscillations. Okay, so this is Wien bridge oscillator. Next we are going to see about phase shift oscillator, that is RC phase shift oscillator. So the next type of oscillator that we are going to discuss is a phase shift oscillator. Okay, so there is a RC phase shift circuit on which this oscillator relies upon to have a phase relationship between the input and the output of the amplifier. So the phase shift produced here is 180 degree. Okay, so this is the circuit. The amplifier can have BJT realizations, that is common emitter configuration of BJT, or FET realization is also possible for the amplifier circuit. So this is a general structure of a RC phase shift oscillator. Then the frequency, this is a very important equation, F is equal to 1 by 2 pi RC square root of 6. Okay, and the feedback factor for this RC phase shift circuit is 1 by 29. And we know that as per the BARC criteria, A beta should be equal to 1, and for starting up of oscillations, it should be considered as greater than 1. Okay, so if beta is equal to 1 by 29, A should be greater than 29 to be for A beta greater than or equal to 1. Okay, so this is the condition for a phase shift, that is RC phase shift oscillator, and the frequency of oscillation F is equal to 1 by 2 pi RC square root of 6. This is a very important equation. I have seen question papers asking directly this equation. Okay, so please do note this equation. Okay, so this video will be uploaded as a formula revision video of oscillators, and we'll be covering the important formulas of phase shift oscillator, Wien bridge, Clapp oscillator, Colpitts and Hartley oscillators. Okay, so you can find the full notes of this video in the EC Electronics page of this Facebook page. Okay, so please do follow the page for getting the notes of these videos. Okay, so this is the RC phase shift oscillator. Next we are going to discuss about LC feedback oscillators. So earlier we have discussed about RC feedback oscillators. Now we are going to see LC. LC means, or LC feedback means, the feedback circuit is having inductance and capacitor combinations. Okay, so that is LC feedback. RC feedback means resistor capacitor combinations is present in the feedback circuit. Here it is inductor and capacitor. I hope it is clear. So the main type of LC feedback oscillators are Colpitts, Clapp and Hartley. So this is actually the names taken from the inventors of this or the people who have put forward this idea. Okay, now LC feedback oscillators are generally used for frequencies greater than 1 megahertz. RC feedback oscillators were used for up to 1 megahertz frequency. Now LC is used for higher frequency range of operations. And the first one that we are going to see is a Colpitts oscillator. Now I'll be giving you a trick. I'm going to give a trick for studying Colpitts, Clapp and Hartley. In both three cases, the equations are almost identical, and also the amplifier stage. So our feedback oscillator consists of an amplifier stage and a feedback circuit. The amplifier stage is almost the same for Colpitts, Clapp and Hartley. So you can connect and study very easily. Okay. So while we are discussing, you'll get to know that this is actually very easy to study. So this is a amplifier stage which is realized with the help of a BJT. This is a common emitter configuration which is very familiar to everyone. Okay, so this is a voltage division circuit. Base is this is the collector, this is the emitter which is ground, and this is the common emitter configuration. Okay, so R4, C4, then R1, R2 in the voltage division unit. Pull-up resistor is R3. There is a capacitor coupling for the feedback circuit, which is C3. Now this is a feedback unit or the feedback circuit which is consisting of L and a series combination of C1 and C2. Then it is connected to the output. Okay, so it is actually taken from the output and fed to the input. So this is a very simple Colpitts oscillator. Now the frequency or the resonant frequency, I've given it in a box here. The resonant frequency of this feedback circuit is Fr is equal to 1 by 2 pi square root of L into Ct. Now Ct is the total capacitance of this C1 and C2 combination. Okay, so since it is series connection and since it is capacitance, Ct is equal to C1 C2 by C1 plus C2. That is a series equation. Now there is an LC circuit here and it is having some quality factor, okay, or Q factor, and the resonant frequency is also dependent on this Q factor like this. I have written the equation over here. Fr is equal to 1 by 2 pi square root of L Ct 1 by 2 pi square root of L Ct into square root of Q square by Q square plus 1. Okay, so these are the most important things you should be knowing about Colpitts oscillator. And there is another thing which you have to consider is that here if you see, this is the equivalent circuit of this Colpitts oscillator where we have represented this entire amplifier stage with a triangle which represents an amplifier. And you can see there is a Zin written inside the triangle which is representing the input impedance of the amplifier which is acting as a load to the feedback unit. Okay, so this input impedance will act as a load. It will have a negative effect or acts as a load to the feedback unit. So in order to represent that, this Zin has been represented, or you can consider this as an equivalent circuit of Colpitts. Okay, so that is the case. Now we have discussed that the input impedance of the BJT is having a negative impact on the feedback circuit, and what can we do to reduce this feedback, that is what can we do to reduce this effect of input impedance, that is what can we do to reduce the load on the feedback circuit. This can be achieved, I have written here, this can be achieved with the help of a transformer coupling. That is, if you place a transformer in between these two units, then the load will get actually reduced, okay, or the effect of input impedance of the BJT will be reduced. Okay, so this is the most important things about the Colpitts oscillator. I hope you have understood the circuit and also the resonant frequency, the equivalent capacitance, and also the dependence on of the quality factor on the resonant frequency. Now, if you have this circuit, this is very easy for you to study the Clapp oscillator circuit also. Let's see that nextly. Next type of oscillator that we are going to see is Clapp oscillator. So I have just replaced this circuit, which is a feedback circuit, with another series capacitor. So that is the only difference between a Clapp oscillator and a Colpitts oscillator. In a Clapp oscillator, which is actually a variation of Colpitts, the difference is additional capacitor C3 in series with the inductance in the feedback circuit. That is the only difference. Now, according to this C3, the equations will be slightly varying. So, you can actually relate the Colpitts and the Clapp oscillator if you are preparing for any competitive examinations. You can study it relatively. Okay. So, this is a circuit. There is an amplifier stage. There is a feedback circuit which is having 3 capacitors and a inductor. Okay. The resonant frequency equation will be like this. This is CT. Okay. So, the resonant frequency FR is equal to 1 by 2 pi square root of L into CT. Now CT here is now changed as 1 by C1 plus 1 by C2 plus 1 by C3. There is an additional C3 for Clapp oscillator. Now consider that when C3 is very much less than that of C1 and C2, this is C2, okay, not C3. So if C1 is less than, if C3 is less than C1 and C2, then the resonant frequency is entirely controlled by C3. That is, FR will be now equal to 1 by 2 pi square root of L C3. Okay, so that is the change when C3 is selected lesser, very much lesser as compared to C1 and C2. Okay, so that is Clapp oscillator, and it is more accurate and gives more stable frequency oscillations. So this is the only difference between Clapp and Colpitts oscillator, and these are the equations. Okay. The next type of oscillator is Hartley oscillator. So here again the circuit is almost similar. You can see that in the earlier one also there is a capacitor given at the output. It is just used for output coupling. There is no effect on the feedback circuit or on the overall working of the circuit. Okay, so just these capacitors are introduced for coupling purpose. Okay, even if you don't draw this in the circuit diagram, there is no much effect. Okay, now this is the feedback circuit. And also in the earlier Clapp diagram, I think I have marked this as C4 or C5. So please do correct, there was a C4 here also in the earlier figure. So please give different names, okay. They are not identical. Don't confuse them as identical, they are not. Okay, just they are used for coupling purpose here. Okay, now for the Hartley oscillator, this is the feedback circuit. Here the difference from the earlier oscillators is that earlier we have connected capacitors in series, but here you can see two inductors are connected in series, and connecting to this combination there is a parallel capacitor. Okay, now the resonant frequency is FR is equal to 1 by 2 pi LT into C. So this LT is the suffix, so the equivalent inductance. So for equivalent inductance, LT is equal to L1 plus L2 since they are connected in series combination. Okay, so this is the circuit of a Hartley oscillator, and here the feedback factor beta equal to L1 by L2, and for having sustained oscillations or for satisfying the BARC criteria, AV should be equal to L2 by L1. Okay, so this is a Hartley oscillator and this is a circuit diagram. So the only difference is that the difference in Clapp, Colpitts and Hartley oscillators is only in the feedback circuit. In the case of the first one which we have discussed is Hartley oscillator, there you can see a capacitor connected, two capacitors connected in series with the combination of inductance. In Clapp there were three capacitors. In Hartley there are two inductors connected in series. So that is a difference. So in these three oscillators, the amplifier stage is almost same or exactly same, you can say. Okay, now in some figures you can see this coupling capacitors, in some figures you cannot see. This is generally representing an amplifier stage. Just know that this is an amplifier stage and we are using a common emitter configuration, and you have to use the common emitter configuration if you are using BJT. You may have a FET combination also, but generally you can see a BJT common emitter amplifier stages only, and these stages are being used same in Clapp, Colpitts and also in Hartley. The difference is only in the feedback circuit, which actually varies. Okay, so in Hartley there are two inductors connected. In Clapp there are three capacitors. In Colpitts there are two capacitors with a inductor. Okay, so these are the important oscillators which we are discussing in this video. So we have discussed about Wien bridge oscillator, RC phase shift oscillator, Clapp oscillator, Colpitts and Hartley oscillator. So these are the most important terms or the names which we hear when we are talking about oscillators. So this was actually a formula revision and a quick revision video of oscillators. So I really hope that this is useful for your preparation. Please do share it maximum with all your friends who are either gate experienced or any competitive exam preparation, if they're preparing, please do share it. And if you found it useful, please do give it a thumbs up. And if you want more videos, please do subscribe to the channel. Thanks for watching and keep on watching.